Hello everyone. In this content video, we're going to talk about the average atomic mass for elements. It's listed on the periodic table. And to me, this really belongs in chapter 2 when we're talking about isotopes. But in this book, it's in chapter 3, as if we needed more calculations in chapter 3. They include this one here, but that's the way it goes with this book. All books are different. None of them are perfect the way I would like them if I was emperor of the chemistry world, but it's pretty good. Anyway, just a reminder that mass on the periodic table is the average mass of an atom in AMU based on what percentage of each isotope you have in their natural abundance of those isotopes. And so what we need to be able to do is calculate the average atomic mass based on that. And this is the first section of chapter 3. And so we're going to do it just by using an example. And so the example that I have is for gallium. And I chose that one because there's only 2 isotopes. And that way it's not quite so complicated. And so when you look, it doesn't take up so much space on paper. So when you look up these isotopes, there's one isotope that would be gallium-69. It has an exact mass of 68.92558 atomic mass units. And that one is present at 60.11%. And then the other isotope would be gallium-71, which would be an exact mass of 70.9247,050. It's amazing how accurately and precisely they can measure these isotope masses. And then, of course, that means the rest of that, since there's only 2, would add up to 39.89%. So those are the 2 isotopes. And I've taught students how to do this calculation to get the average atomic mass a million different ways. Well, maybe not a million, but a few different ways. And I finally decided that none of the ways that I thought were helpful in explaining it were really all that helpful. And so, I think if you get fractions, you won't have any problem with this, and it's a weighted average. So obviously, if it was 50% of each, we just add these up and divide by 2 and we get the average, right? But it's not. There's 60% of this one, and so we have to factor that in somehow. And so one way I used to do it was consider, well, what if we had 100 atoms? Exactly 100 atoms, you would say 60.11 of those have this exact mass. And of course, you can't have a fraction of an atom, but you get the point. And then 39.89 would have it. And then you would divide by the 100 atoms at the end, and you would get it. I thought that might be helpful conceptualizing it, to think of if we had just 100 atoms. But really, we have, Avogadro's number of atoms maybe in a sample. So instead, I just have, since it didn't seem like the various ways of calculating it were all that helpful, I'm just going to show you the way that you'll have to just remember how to do it. And if you get fractions, you'll be able to do it. So all we do is we take these percentages and convert them to their fractional components. So this divide by 100, right? So the fraction would be 0.6011 and 0.3989. And then you just multiply each fraction times the mass of the isotope and add them together. And so if you'll just have to remember. I thought the other way maybe students could do it without having to memorize anything. But anyway, so that's not too hard, even if you have more than 2. So let's just go ahead and do it. So we'll take 0.6011, the fraction of gallium-69, times its mass, 68.92558 AMU, and then add the 0.3989 times 70.9247050 AMU. We just add those together. Okay, so I'm going to grab I found my favorite calculator because it's got the styling orange. Uh-oh, batteries are dead. Oh, no, there it comes. Maybe it'll work. 0.6011 times 68.92558 plus 0.3989 times 70.9247050. Hit equals, and I get 69.72303096. Now, do you need all that? Not necessarily, right? And obviously these ones, the way we program them on WebAssign, they're a little tricky, right? Because we do our rounding. You could never get the wrong answer if we just leave it at our usual 3 digits, the rounding error of 1%. And so when you get a question like this on the homework, make sure you check to see what it says. It's going to tell you, if I programmed it correctly, what decimal place you have to go out to in order to get it right. Okay, so that's how you do the average atomic mass, and hopefully it's not too difficult of a calculation. Like I said, I'd prefer if this calculation was in chapter 2, because we're going to have a lot of calculations in chapter 3, but it happens to be in chapter 3 in this book. And I just want to remind everyone with isotopes what this means. You know, when you look up this mass on the periodic table, so when I look up gallium on the periodic table, what does mine just says 69.72 AMU for gallium, and that's in the front of our Zumdahl book. What that means is that's the average mass of a gallium atom. There aren't any atoms of gallium that weigh that much, right? They either weigh 68.93 or they weigh 70.92. None of them weigh 69.72. Okay? No atom of gallium has a mass of 69.72 AMU. And that's something that you need to accept and remember, that concept, right? It's always reported as the average of the isotopes. All right, thanks everyone. I will see you in the next video.